Guys, what's up? Today, delving into a bit of power electronics, and today the main device which we'll be using is the SCR. It's a very classic, old style device. It's been around for a very long time, and it's used a lot in industrial applications. Because it's a high power device. It can handle a lot of current, and it goes up to kilovolts, so it's good for high power. These days in normal we don't really use it much. We hear is MOSFETs all the time. But yeah, this was the original, the original switch, you could say, that when MOSFETs and BJTs were not around that much. So yeah, today what we're going to be doing is based on this SCR. And the thyristor is basically a family. It includes the SCR itself, and there's a diac, there's triac, so it's a whole family. But generally, the term is used synonymously. SCR, thyristor, the same thing. So it's a four-layer device, NPNP, and PNPN or NPNP, whatever you want to call it. And it has a cathode anode, and you can see the symbol is similar to a diode, but there's this extra terminal here. That's the gate, similar to a MOSFET. So it's a controlled switch. Diode is an uncontrolled switch. This is controlled. So that's the main difference. Other than that, it's pretty much similar to a diode. In the on state, it has like a similar 0.7 volt drop across it. So in that way, you could say it's a diode, but it's a controlled diode. So what we're going to be doing today is this: the single phase controlled rectifier, and we're going to be doing half wave. I'm just going to be using one thyristor here. So normally we all know the standard rectifier using the diode bridge. Everybody does it. They just put four diodes together, and you can convert both half cycle, positive half cycle and negative half cycle of AC. You have that pulsating DC waveform. And same thing if you do with a single diode rectifier, you get this positive half cycle, and then you get nothing, and then you get the positive half cycle again. But the thing with the diode is, as I said, it's an uncontrolled device. You can't really vary the voltage how much you want of this cycle. And normally, I mean, we rectify that with a filter capacitor in a standard power supply circuit, and then maybe put a linear regulator like the LM3170 338. There are many out there. Or maybe if you are feeling different, these days they do a lot of switching circuits, because yeah, power electronics is there. So a buck converter, probably that's what you would see today. But this is another way. If you just let's say you have in this positive half cycle, the average voltage is, say, something like 10 volts, but you want only 5 volts. Now what you could do is use a thyristor and vary what is known as the firing angle. So you can, up to that firing angle, the output is going to be off. There is not going to be any output once you give that firing angle. And basically at the firing angle you give a pulse. That's what I mean by the firing angle. A single pulse at the gate of the thyristor, and then yeah, this turns on, and it will conduct, it will continue, it will follow. You can see we gave the firing angle here. Up till then there was no output. We gave the firing angle. It continues your input sign till pi, and pi is your zero crossing, where it goes into the negative half cycle. And since we are only doing the half wave here, it naturally commutates, and what they call as natural commutation, because the SCR turns off. Because I won't go too much into why, but yeah, there's something called as the holding current, which is a minimum amount of current which you need to keep the SCR in the on state. So if it goes below that, and it depends on the data sheet, but let's say something like 30-40 milliampere, if the current goes below that, and of course at this point with a resistive load, it is going to go to zero, it's going to turn off. So your output is again going to go to zero, and then the whole cycle repeats depending on your firing angle. Again it's going to come and it follows. So this is what is controlled rectifier basically. So by varying, if you give this firing angle very early, you get the same, essentially the diode one. But let's say you give somewhere here, let's say 90 degrees, pi is 180. So if you give it 90, pi by 2, you get half of the average voltage. Same, the RMS voltage, both of them vary. If you give something like pi as the firing angle, you're not going to get any output. But yeah, as you vary the firing angle, you're going to get a different average output voltage. So today, to demonstrate this, normally you have those firing modules in the labs and all. They give you the pulses, but you don't really know what is going on behind. It's just a black box. So that's why I thought of making a circuit to demonstrate that. And you could, go for the analog domain or the digital domain. The microcontroller is always easier in the sense that you can code all your logic because it's embedded. But I am working on that currently. Probably the next video will be on that. Let's see. But currently, I just thought of going the classical way and doing it in the analog domain. So we have it here in multisim. This is the entire circuit. I'll just zoom out. Yeah, it's a bit big. It's in multisim, but I'll just break it down so that let it just gets clear, because I made this circuit part by part, and by the end, and you'll see later on the breadboard, everything is on the breadboard again. It did get a bit big and tough to debug, so it's better to understand it stage by stage. And this is completely analog. There's no coding involved here. It's fully using discrete ICs and all of that, and RC mainly. So first off, yeah, let's go into how we are gonna do this exactly. We need our firing angle, as you know here, it needs to be synchronized with our grid sign. So what we do is we step down the sign as they have shown here. We don't want to work with 230 volts directly. It's a bit dangerous, and we don't have any need for that. So maybe step it down to like 12 volt, 9 volt, something like that. And after that, that is going to be our input sign. And what we do is we need to detect when that zero crossing is happening, because your firing angle starts from the zero crossing. So that's what you do here. I have my 15 volts step down sign, and what I'm using here is the 6N137. It's a high speed optocoupler, because again we want to separate. This is more of a high power AC side. We want to separate it from our low power logic side. So we use an optocoupler, and what this diode is basically, in the positive half cycle it's going to conduct. And I won't go into how the optocoupler works. I made a video on that before. So it is going to give a, when this goes high basically in the positive half cycle, this is going to go low, because it's AND gate here, you could see it, but generally it's a photo transistor. But yeah, either ways, this output is inverted, and in the negative half cycle, I mean it's a diode after all, but just for safety I just put parallel. So in the negative half cycle, this diode is going to conduct, so nothing with the optocoupler as such. So we are only concerned with the positive half cycle. So what we do here is, after that we get this, it's going to convert our sine basically into a sort of square wave output, you could say inverted square wave. And square waves are easy to handle with, you can just classify it as a high or low. Sine, it varies over time, and yeah, that's a little tougher to handle. So digital is good, we convert it, and this runs on 5 volts. It's a logic level optocoupler. After that, what we do is, these two RCs which you see, this is a pull up, same for the phototransistor, and this RC which you see, these two are in series. This is a pot, and this is to vary the firing angle. As I said, you want to vary it from 0 to 180 degrees, and this R and this R is in series, and this C basically, this is your RC delay. It's you could, it's basically RC delay. Yeah, so to delay when this pulse goes to the next stages, we have a RC delay here. Minimum there's a 1k. If you keep this pot at 0, there's going to be R is 1k and C is 470 nanofarad. So if you, the calculation is 0.693 RC, that's the standard time constant calculation to classify it as high or low, and that generally works with CMOS, which is what we're going to be using here. This is an inverter, the CD4049. It's a NOT gate, and as I told you here, the output is going to be inverted. When this positive half cycle is there, this is going to go low, but we want the non-inverted output, so we invert it again. So if you do two inversions, you're going to get back the original output, and that's what we're going to have here. We're going to have the non-inverted square wave output here, which is delayed. So that's up till here, this point. After that, what you have here is, you can see here it was series R, cap to ground. This is series cap, resistors to ground. So what this is basically a RC differentiator. So the ulta of this RC differentiator basically is, you give a square wave, it works on differentiation, how mathematical works. When there's a sudden change, it's going to give a small pulse. There's going to be a small peak, and when it goes in the what do they call it, the rising edge, there's going to be a small peak, positive peak, and after that it stays constant, and we know differentiation of a constant is 0, so there's going to be there's going to be ground, your output. After that, when there's a negative falling edge, there's going to be a negative peak. So that's why we need the differentiator, and here all we need is a single pulse. We don't need this entire square wave converted from the sine. So we need that RC differentiator here. And I'm only concerned, since I'm doing only a half wave here, I only need the positive half cycles peak. So that's why I have this diode here. So it's going to only allow the positive peak to go. The negative peak is going to be reverse biased, and we want that. So at this point, after this, we go here to this stage, which is basically you could say the second last stage. This is a 555 classic. It's in the monostable condition, or monostable multivibrator as they call it, because we wanted the pulse to turn on the thyristor. As I said, it needs a small pulse of sufficient gate width. So the time width should be depending on the datasheet again, but I've taken around 500 microsecond, and that seems to be working. But yeah, sometimes you need more, it depends on the surroundings and all of that again. But yeah, for me 500 worked. So I've designed this RC values 1.1 RC for the 555 to give me a 500 microsecond high. Once this trigger goes low, normally it's pulled up, that's standard how 555 works. And once this small positive pulse comes, this it's just a small NPN inverter, it's going to give a small low. And because we need a small touch to ground to turn this monostable 555 on. Normally it's pulled up, so once this gives the small positive pulse, this is going to get grounded, and this trigger is going to go low, you're going to get that pulse. So this is the main pulse circuit together. So we have, just to recap, we have the optocoupler, we have the RC delay, we have the inverter, we have the RC differentiator, and finally we have the monostable multivibrator. So this is going to be your small pulse, and this pulse is going to vary with respect to time depending on how you change the pot. You increase the resistance, is going to go more, and you're into this side, towards this side, and your average output voltage is going to reduce. So up to this point. And another thing is, now moving on to the power circuit here, which is smaller, shouldn't take much time. There are what they call these pulse transformers. They're small 1:1 transformers, and again same thing, to isolate on our monostable side, to give this pulse to the thyristor. Again, this is a low power circuit. Again, we want to keep it isolated from this thyristor, which is a high power device. So just a resistor to limit the current, because after all it's DC. If you don't use a resistor, it's going to get shorted, and yeah, that will be messy. So this is not a AC signal we're giving here. It is AC in the sense that it's varying with respect to time. It's a switching waveform, but it's not AC in the sense the voltage is changing every second like sine. So we do need to put a series resistor here, and same thing on the other side to limit the current on the thyristor. This is the gate, this is the anode, and this is the cathode. The cathode is going to be common with this transformers, whatever, this secondary windings, this one. And again, I'm using the same 15 volts, since same thing I said, we're not going to be working with the 230 volts directly. I'm just going to show you the waveform with a 100 ohm load. And yeah, depending on how you give the firing angle, average output voltage across this load, this 100 ohm, is going to change. So yeah, that was the entire circuit together in the analog domain, and now we can go to the breadboard circuit. So we have the breadboard circuit here, and I always I say that preferably don't do these power circuits on breadboards, but it's become old me saying that again and again, and I still repeat it because it is easy. You can't deny that prototyping with a breadboard is easy, and it doesn't take much time. So yeah, let's see how it goes. But anyways, to go on with the demo, everything is being run from this 12 volt supply, as I said. And the logic level optocoupler, I said you cannot give 12 volts to this. This runs on 5 volts, so a small 7805 here. So starting with the transformer, we have the AC connection here of the grid, and the transformer which is going to step it down to 15 volts or 14, whatever. And there's the optocoupler and this is our other side. So now this AC side is isolated from this, so it's protected. After that, it goes on here to this stage, and you don't need to worry about this. You know, this IC here, this is another 555, but that was for another thing, so that's not really a part. Only this IC onwards is the actual circuit, so ignore this part. So it goes on here to this, yeah, it goes on here as I showed, the resistor, series resistor, and the pot to vary the firing angle. It's a 47k pot. And after that we give it here, this is the inverter, the CD4049. And after that it goes here to the RC differentiator, that 1 nanofarad cap you see there, that's for the differentiator. And after the RC differentiator, it's going to go through the diode, the 4148 small signal diode, and it goes to the inverter, which is here, the BC547, and finally the monostable 555 over here. So the output of this is what I called as pulse in the schematic over there. So that pulse is this yellow wire which is going on here to this third breadboard. So you can see the first breadboard is for the optocoupler, second is for, you know, the making the signal, third is for the power circuit, you could say. And yeah, here after that it goes here to this small, as I said, this is what the pulse transformer, a small circular one, and 4502 they call it because there are two windings. It's a 1:1. So the series resistor, this is our signal which is coming from that breadboard. And on the other side here you have the output which is going isolated to the thyristor. So this is the thyristor. I'm using the TYN1225, which is a 1200 volt 25 amp rated thyristor. So it's, you can clearly see the ratings have gone. You can just calculate the power, how high power it is, and I'm definitely not pushing that power, but nevertheless, yeah, it's a high power rated thyristor. And yeah, this is the 100 ohm load, as I said. And yeah, it's going to be dissipating at least 1 or 2 watts, I believe, if you calculate. So yeah, we can't use those, you know, these puny ones like half watt or the quarter watt, they'll just burn out. So yeah, this is a power wire wound resistor, 10 watt, so we should be good. And yeah, that's the thyristor, I already said that. And we'll view the you know, the waveform on the oscilloscope. So I'll just turn on the circuit here once. I'll turn on the oscilloscope, and yeah, I'll just turn this on. And yeah, you can see the waveform here. As you see, the positive half of the cycle is being converted, negative half cycle there's nothing, because as I said, we're doing only half wave control rectifier. So you can see once that firing angle comes, if I just zoom in a bit, you can see there's that sudden step change, and that's exactly how it's going to look. Let's continue with the sign and commutate at the zero crossing. So that's how it is. And now with the main point of the thyristor, different from the diode, is the firing angle control. So you can see here I'm going to vary the spot, and currently you can see RMS voltage is around 8.6 volt, and now I'm going to change the firing angle. And yeah, you can see here I'm rotating this spot here, and yeah, somewhere here, and you can see the RMS voltage reduced because I increased the resistance and the firing angle got delayed, the delay angle went more. And let's reduce it further. You can see even more. Now we have like 5 volts RMS, earlier we had 8 volts. And let's go further down somewhere here, and you can see 4 volts. Now we're almost at half of what we had originally, so the rest half is not being converted at all. And that's good, you know, because we are only taking how much power we need, and sometimes that's good in industrial applications. So if I go even further, I'm delaying it even further, it's gone 3 volts almost. And suddenly, this is the thing with the analog domain, the tolerances and all are there. So you might not get a very perfect output, but you can see here, if I am varying the angle too much, delay, it's almost going, now it's become very less, almost 2 volts. And yeah, it's disappearing a bit. I think it's something with the signal, but yeah, nevertheless, you could see that if I go very low into the delay, practically there's going to be no output voltage because it's going to go almost 180 degree, and then the thyristor is never going to turn on. So you can do that too, but yeah, let me increase the voltage again in the other direction. And you can see the RMS voltage is increasing again. So yeah, that was the whole point of the control rectifier here. You can with the by controlling the delay angle, you can control your average voltage as well as your RMS voltage. So we went low here just to show you again once more. Now we just have a small peak here, and yeah, gone here. So going back to the original waveform, this is the you could say this, if you give a firing angle of 0 degree, ideally you should get, you know, your diode output. And here it's not exactly the diode output, because I think mine still has a delay of 1 millisecond, whether you like it or not. And I don't know if it that's those are the propagation delays adding up the gate, because we are using a optocoupler is fast, that shouldn't be a problem, but we're using one gate here. The RC themselves has some, so the latency might be the issue here. So we, even though we don't want the firing angle, we want it to be 0, there is still a small part of the sign which is getting chopped off, but nevertheless you got the point with the controlled rectifier here. And yeah, that was the whole point. And we could do it in the analog domain, which is impressive, because in the digital domain, you know, you just code up that is, I'm not saying that that's easy, and I do know that, because I'm still stuck in the code a bit. So everything has its own merit. So you know, analog, we don't have to, the resistor is getting a bit hot here, so I'll just switch this off. But yeah, all the analog, digital, everything has its own merits and, you know, flaws. But we should learn, you know, to appreciate all of them as, you know, electronics engineers, electrical. So yeah, that was the demo here. I hope you know learned a thing or two, because I surely did, making this circuit. And you know, it spanned over three breadboards here, so I got confused in the middle. And you know, these wires keep getting open circuited. That's a classic problem with these DuPont wires. But yeah, enough with my rant. The circuit worked, and I'm happy about that. And yeah, I hope you like this video. So yeah, thank you.